Okay, so I'd like to finish up rotational motions and Newton's second law by doing an example. Let's say that we have a roller coaster that has an upside down loop. So the roller coaster is going down a hill and it's going to go around, upside down, and around this loop. So with a roller coaster, the wheels on the roller coaster car actually are attached to the track so that if the roller coaster were to stop when it's going upside down, it wouldn't fall off. But ideally, you don't want the roller coaster to even want to fall off when it's going around the track. So it's got to stay in contact with the track the whole time. It's got to be going fast enough that it stays in contact with the track. So the question I want to ask is, while the roller coaster is going around the loop, where is it most likely to lose contact with the track? If it wasn't attached to the track, where is it most likely to lose contact? And you should take a second to think about how could you possibly answer that question. But I'll give you a hint. You can pause it and think about it, but I'll give you a hint, and that's what does it mean to be in contact with the track? In terms of Newton's laws, what does it mean to be in contact with the track? And what it means, I'm going to tell you now, is that the normal force must be greater than zero. So really, in order to answer this question, where's the roller coaster most likely to lose contact, we're asking the question, where is the normal force the minimum? And answering that question, this is the same question as the ball on the string and asking where is the tension in the string a minimum? It's the same question. And the tension in the string was a maximum, remember, at the bottom and a minimum at the top. So that means that, and you could go back and look at that problem in your notes, that the roller coaster car at the bottom of the loop has the largest normal force and at the top of the loop has the smallest normal force. Now, this is relevant to real-life experience. Just think about, real-life experience riding a roller coaster. Think about riding a roller coaster and think about how it feels when you're going over hills and upside down, things like that. What happens is that sometimes you feel heavier and sometimes you feel lighter and sometimes you even feel weightless on a roller coaster if you're in or close to free fall. And what does it mean to feel lighter or heavier? It means that the normal force changes, right? The normal force, if you're sitting still or if you're not accelerating relative to the surface that you're sitting on, the normal force is equal to your weight. But you can do things like ride in an elevator up or down or go in a circle, and the normal force is going to be greater than or less than your weight. And the way how heavy you feel is equal to how hard the floor is pushing on you. How hard the floor is pushing on you is equal to the normal force exerted on you. So where the normal force is the largest at the bottom of the loop, that's where you feel the heaviest. And where the normal force is the smallest at the top of the loop, that's where you feel the lightest. But also notice that if you go around the loop fast enough, you can keep the normal force large enough that you never feel like you're weightless and that you never feel like that if you just close your eyes actually in a roller coaster in an upside down loop, you won't even know you're going upside down because there's still a normal force on you pointing from your butt to your head in the same direction as if you were sitting still. So you may not even know you're going upside down if the normal force is large enough. So the next question is then, if the normal force is the least at the smallest at the top of the loop, then how fast should you be going at the top of the loop to remain in contact with the track? And that means that question then indicates that you should be going, that's where your minimum speed is going to be, and you should always be going faster than that. And we can also determine, therefore, how high should that first hill be in order to make sure that you're going fast enough to get around the loop. Right? The higher the hill, the faster you're going to be going at the bottom of the loop, the faster you're going to be going at the top of the loop. That question is going to be asked next week in next week's video lecture. How high, how high you need to start from in order to get around the loop. But right now, we're asking the question, what is fast enough? What is fast enough? How fast should we be going at the top of the loop? Well, let's go ahead and solve this as a Newton's second law problem. And of course, the first thing that we need to do is at the top of the loop with my roller coaster car upside down, what is the free body diagram? We go through our forces, same solution every time. We go through our forces. Is there a tension? No, there's no strings attached. Is there a spring force? No, there's no springs attached. Is there a normal force? Yes, we are in contact with the track. What direction is the normal force? It's away from the direction of contact. So the normal force is in the downward direction, towards the center of the loop in this case. Always towards the center of the loop while you're in the loop. Is there a gravitational force? Yes. The roller coaster cart has a weight. And is there a frictional force? Sure, there are frictional forces, but the frictional forces are perpendicular. They're left and right. And we're not going to care about those. Or we could just say it's a frictionless surface. We don't have to worry about friction in this case. So, whoops. And then we ask, is there an additional hand on the thing pushing it or pulling it that we can't really categorize as a tension or normal force? And the answer is no. So we've gone through all our forces and drawn our free body diagram. Next step, as always, nothing's changed here, is to choose a positive direction as the direction of acceleration. And the acceleration is towards the center of the loop. So I'm going to choose that as my plus x direction towards the center of the loop. Of course, we are talking about this guy here. Next step is to write down Newton's second law. I'll do that on a new page. Write down Newton's second law. So F net equals ma. And the only forces are in the plus x direction. So it's a one-dimensional problem in the plus x direction with our forces being plus Fn plus Fg. They're both in the plus x direction equals, that's the left-hand side, right? We always solve the left-hand side, then we solve the right-hand side. M, I did not give you a mass of the roller coaster car. Let's see if we need it. If we do need it, then we can just estimate the mass of a roller coaster car. Imagine maybe it's 500 kilograms or so, with people in it or without. And then the acceleration. This is an object going in a circle, so we always replace for an object going in a circle acceleration with v squared over r. So we solve the left-hand side from the free body diagram. We solve the right-hand side, put in what we know, and leave blank what we don't know. So acceleration is v squared over r. So F net equals mv squared over r. F net is the normal force plus the gravitational force. So this is an appropriate equation describing the roller coaster car at the very top of the loop. So then the question is how do we answer the question? How fast should you be going at the top of the loop to remain in contact with the track? So let's look at this equation. What does it mean to remain in contact with the track? Think about that for a second. So you can always pause it and answer a question for yourself, and you should do that. But what it means is that Fn is greater than 0. If Fn is equal to 0, or if you do a problem and you find out that Fn is negative, what that means is that Fn was actually 0, right? It means that it shouldn't exist in the problem. But if you're in contact with the track, remember all of these forces are actual magnitudes. They're magnitudes. The signs are put in explicitly as those plus signs out front. So Fn must be a number greater than 0 if we're in contact with the track. At what point do we lose contact with the track? Fn can get smaller and smaller. We can go slower and slower. And look at the relationship here. If you look at the right-hand side, oops, that just crosses it right out. That doesn't work very well. If you look at the right-hand side of this equation, and you can see as v gets bigger, since Fg is a constant, as v gets bigger, Fg is a constant because it's the weight of the roller coaster car. And as v gets bigger, if we got somehow the cart to starts in a higher hill, so it's going faster and faster when it gets to the top. That as v gets bigger, then Fn gets bigger, right? So the question is what is the minimum velocity for which there is still an Fn? And that minimum velocity is when Fn is equal to 0. So when Fn equals 0, as soon as v gets small enough that Fn equals 0, therefore we have lost contact. Therefore, we can plug in Fn equals 0 and say that's the minimum velocity. We have to be going faster than that in order to remain in contact. So we can just solve for v minimum. And we never plugged in for Fg, so therefore v minimum is equal to the square root of Rg. Oh, it looks very similar to something that we got before, right? All these problems are the same. I think this was when we were looking at the car going around the curve and what was the speed limit of a car going around an exit curve. It's the same answer, same reasoning, same kind of reasoning. Same kind of answer. Of course, I never gave you any constants to begin with. We would have to ask, so you can see from this answer that the minimum velocity that the car has to be going to stay on the roller coaster track is dependent on the radius of the curve. So now you say, oh, well, so what I need is to know the radius of the curve, and you can go and look at a standard roller coaster and ask, what is the radius of a standard curve? And sure, they vary. But let's say that the radius of a roller coaster curve that we're going upside down on is 10 meters. And I'm just saying that's a given. I didn't give it to begin with, but let's make that a given. And if G is 10, okay, therefore V minimum is equal to R is 10, G is 9.8, and so the square root of 980 is about 9.9 meters per second. So we have to be going 9.9 meters per second. That's the slowest that we can be going around that roller coaster loop. Everywhere else on the loop will be going faster. Slow down to get to the top, speed up to come back down. Okay, so then the next question is how high a hill, if a roller coaster is powered entirely by the hill that it comes down, which roller coasters typically, not always, but typically are powered by that first big hill, how high a hill do I need to be on in order to be going 9.9 meters per second at the top of the loop? That's the next question. Okay, just keep that in mind. How high a hill do I need to start on? Let's go back. How high, right, of a hill do I need to start on in order to be going fast enough at the top of the loop? That was what I put in green here. And that's what we're going to answer next week with energy conservation. We're not going to do that with Newton's second law. We're going to do that with energy conservation.